So we've got our scales for both the x momentum and the y momentum equation now. From the x momentum equation, we have the inertial forces, or u infinity squared over L, pressure forces 1 over rho p over L, and viscosity forces nu u infinity over delta squared. The size of the y momentum size of the forces in the y momentum equation are delta over u infinity squared over L squared, 1 over rho p over delta, and nu u infinity over L delta. The y momentum equation scales can be rewritten by pulling this delta over L out of the inertial term and the viscous term. So we can see that this term here is delta over L u infinity squared over L, which is the same as this term just multiplied by delta over L. So that means that this inertial force, the inertial forces in the y momentum equation, are much, much smaller than the inertial forces in the x momentum equation, because this delta over L, of course, is very small because delta is much smaller than L. Similarly, the viscous forces have the same form as well as the x momentum viscous forces, but they're also just multiplied by delta over L. So both the viscous forces and the inertial forces in the y momentum equation are significantly smaller than those forces in the x momentum equation. What we're going to do now is make use of that fact to try to deal with pressure, because we really haven't been able to do anything with pressure. Now, in order for it is true that this system has two forces that matter and one force that doesn't, but we don't yet know which is which. So we still have the three forces: inertia, pressure, and viscous forces. And I'm telling you that two of them are significant and one of them is not. But that's what we're going to try to show so that we can just balance two forces, not three. So what we're going to do is assume that we know the answer first. Maybe pressure is balancing inertia. So maybe that's what's happening in this flow. So we're going to just look at the pressure and inertia forces. So here's the pressure scale in the x momentum equation. So we're going to say, okay, it's 1 over rho times p over L. Now it's not p here, it really should be delta p x. That is the amount the pressure changes in x. Because as I said before, p doesn't go to zero anywhere in this flow, and that's a common mistake, is to assume that the pressure is going to go from P infinity to zero. Well, that's not going to happen. This is asking dp dx is how much does p change. So this really should be delta p all the way along here. So we have delta p in the x direction, and if it's balancing inertia, that means it's balancing this term. So it's going to be balanced u infinity L squared over L. So we can get a sense for the size of the change of pressure in x, and it's rho u infinity squared according to this equation. All right, well, that actually makes sense because we know from the Bernoulli equation that that's typically the same thing, and it's the same type of, it's a pressure inertia balance with no viscosity. So then you look at the y momentum equation, and in the y momentum equation you have 1 over rho p over delta, and if it's going to balance inertia, it's balancing this term, delta over L u infinity squared over L. If you solve that for the pressure difference in y, you find that the pressure difference in y looks like this: delta squared rho u infinity squared over L squared. Okay, so how does that compare to the x momentum equation? Well, the pressure change in x, as we said here, is rho u infinity squared. This is the pressure change in y is of order delta over L squared rho u infinity squared. So look at that. So it's hugely, hugely greater in the x direction than it is in the y direction. That is, there is very, very small pressure variation in the y direction, basically insignificant. Well, that's interesting, because if you look at the flow in the y direction, the pressure up here is just P infinity. If the pressure if there's no pressure variation in the y direction, that means the pressure can't vary here in this direction, and the pressure doesn't vary in this direction at all in the free stream. So what this equation is telling you is that there is no real pressure change in the y direction, and because the pressure in the above, in the upper y region, is all P infinity, the whole pressure and the whole flow is going to just be P infinity. There's going to be no pressure change in this flow if it is the case that pressure is balancing inertia. So that might be the case, but what if it's not the case? What if pressure is not balancing inertia? What if instead what's happening is that pressure is balancing the viscous forces? What if pressure balances viscous effects, viscous forces. So it's not an inertia pressure balance, it's a pressure viscosity balance. In that case, we again have from the x momentum equation, looking at the scales, which we have here, we have delta px over L 1 over rho is then going to have to be equal to of the same size as nu u infinity over delta squared. So delta px is of order, well, that's going to be mu because it's nu times rho, and it's going to be L over delta squared u infinity, and then that's times mu if you want to do it that way. So rho times nu. So delta py, based on the y momentum equation, we have 1 over rho delta py over delta is of order delta over L nu u infinity over delta squared. So that's going to give you delta py, which is of order, again, we're going to have mu, because rho is going to come over. We're going to have delta squared over L, delta squared over L, mu, u infinity over delta squared. So that's going to cancel. The two delta squareds are going to cancel. And so we have delta py is looking like mu u infinity over L. So this one, again, delta py, mu u infinity over L, compared to this one, delta px, which is mu u infinity over, if you want to put it over the same kind of L, you'd have to put this as L over delta squared. So again, if it's balancing viscous forces, delta px, L over delta is huge. Delta px is hugely, hugely greater than delta py. So delta px is hugely, hugely greater than delta py. Whether or not we're balancing viscous forces with pressure or inertial forces with pressure, we find in both cases that the scale analysis tells us that the pressure variation in y is essentially 0 compared to the pressure variation in x. But the pressure variation in y is 0 means that all the pressures have to just equal P infinity, because P infinity is the pressure above the viscous boundary layer throughout the flow. So if there's no pressure variation in y, that means there really can't be any pressure variation in this flow. So pressure is P infinity everywhere. And that tells us then that this flow is a balance of viscosity effects and inertial effects, and pressure plays no role at all.